Today I'd like to talk to you about speed of waves, and we're going to keep it really simple today. We're not going to get into sound waves or light waves. I just want to talk in general. And I want to remind you this is a transverse wave, and you can see that the particles are moving up and down. The energy is going left to right. We want to know how fast is the energy moving. We don't care how quickly these particles are going up and down. That's not what we're talking. We're talking about how quickly does the energy get from the spot where it starts to the spot where we're detecting it. Okay, speed of the wave. How quickly does the energy travel? Transverse wave, longitudinal wave, same idea. We have our energy traveling from left to right. The particles are oscillating back and forth. We don't care about that. We care how quickly the energy goes from the left to the right. Okay, so as that energy travels, how quickly is it moving? How many meters per second? Today, we're only going to focus on waves on a string like our guitar. We want to know how quickly do these pulses of energy travel through the string. Okay, so when we have our guitar, we wanted to know what were the factors. And we talked yesterday that the two factors are the linear density of the strings and how tightly we make the tension in the string. So those are the things we want to focus on. Now in real life, this happens very quickly. So we can't really see this happen with our eyes. We can slow it down with photography, but we did it in the virtual sense so we could see it even better. We plucked the string. We watched the energy pulse move through the string. We stopped it at a certain spot, and we found the speed, distance over time. We saw that if we use two different strings with the same tension, we saw that the speed changed as a result of the density of the string. We found that as the density got higher, our speed got lower. Okay? So you could see when it was really low density, it traveled fast. And when it was high density, it traveled really slow. It turned out to be an inverse square root graph, which means it takes 4 times the density to cut the speed in half. We can see it real easily. If we have a density of 1, we have a speed of around 160. If we want to go down to 80, we've got to go to 4. So from 1 to 4, that's 4 times more density, and the speed got cut in half. The next thing is we put all the strings the same, and we put different tensions on different strings. So this time we wanted to see how did tension affect speed. And we saw that higher tensions gave higher speeds. It was not linear. It was not proportional. We saw that it came out to be square root. We can see that if we're at 10, we've got a speed of around 90. And if we go to 40, we got a speed of around 180. So 4 times the tension to double the speed. All right, so that was our speed versus tension graph. We can combine these two graphs and get our equation. The speed of the energy pulse is equal to the square root of tension divided by linear density. This bottom term is really linear density, so don't treat it as two different things. Find that value first. It's the mass in kilograms per meter of string. These were in grams, but when you're using your formula, you got to work in kilograms. All right? Tension, of course, has to be in newtons. Expect these speeds to be really high for light ropes that have high tension. Here we have an example of the reverse. We've got a really heavy rope with low tension. So now the wave travels slow enough that we can see it travel with our eyes. We can watch the wave travel through this battle rope because the rope is heavy and the tension is low. That's not the case with guitar strings. With guitar strings, the tension is high and the density is low, so the wave travels really quick. And even in super slow-mo, we can barely see the wave traveling. Okay, here are two different ropes. Tell me which one of these travels quicker. Would it travel in the rope with lots of tension or the rope with only a little bit of tension? Both of these are light ropes. How about now if we have the same amount of tension, but we have a heavy rope and a light rope? Where should the wave travel quicker? Where should the wave travel slower? Finally, if you're going to do a math problem with this, we have a violin string, and we're going to send the wave using a bow down the string, and we want to find speed. So I would start by finding the linear density. How dense is this string? It's 5 grams. Make sure you work in kilograms. The string is 1.2 meters long. And then you get your density. When you're doing this linear density, it's always best to do this before you put the string on your instrument. So when you take the string out, you can put it on a scale and get its mass. You can stretch it out and see the length. Obviously, you can't measure the mass when it's already on your instrument. And the other problem is not all of the string will be visible. Some of it is wrapped around the tuning peg. Okay, so get your linear density before you actually put it on the instrument. Then whatever you get for that linear density. Okay, so again, mass over length, 0.005 over 1.2. And then whatever you get, plug it into your formula for speed. Once you get speed, you could then use it in your formula for speed equals distance over time. We're only going to have our wave travel a short distance, 40 centimeters to the end of the violin and back again. So we would put in 80 centimeters, 0.8 meters. And we could solve for how long it's going to take. Again, we don't really care about the speeds by themselves, but they will be important for figuring out what sound comes out of the violin. We'll be learning about that in a week or so. And obviously, we want to make sure the proper sounds come out. The first step in figuring that out is to figure out these speeds. So anyway, on Monday, we'll look at speed of sound, and we'll look at speed of light also very soon.